mean, it's wonderful that it happened, but it's very painful. You know, the reason why we can teach this now and not in 1880 or whatever it logically belongs into science is because that in the 70s or so we got a third leg in science, which was, you know, we had experiments, nature, observations, theories which uncover bits of reality and make it comprehensible to us. And then we got computers, and you know, they'll destroy us eventually, but very, very soon thereafter, not for very good reasons. You know, in the 70s they were cheap enough that places like MIT could actually have computers dedicated just to research. And you can see I'm in particular Euler. They were amazing computers. I mean, they could and develop, you know, they had pi 200 digits already in the late 18th century. They were just astounding. But when it came to using it just to solve equations, it was very hard to do. So, you know, my favorite example comes from 1910 or so. In Oslo, there is a professor who has learned Poincaré's approach to celestial mechanics. Not the qualitative that we are discussing here, but actually how you solve equations or motions to make predictions. And being Norwegian, he's interested in polar light. And you know, that's a simple thing, that's some charged particles moving in magnetic fields. He has what's called amanuensis hands, in other words, graduate students. And he has graduate students compute to understand, you know, how you get the polar light. You would like to know how the charged particle, electrons basically, and ions, how do they move through magnetic fields? Equations are known. And basically, you know, he spends his lifetime and any number of amanuenses get burned along the way. And the result is in Oslo, kind of University Science Museum, but the result is, you know, it looks like this. There is a podium, and then there is a piece of wire. Wow. And a little thing. And that's a trajectory that they've managed to compute in years of work. And today you can presumably, you know, it'll take you a month to learn the stuff, but then it'll take milliseconds to compute that much. And you'll be able to simulate many particles going through. So, you know, his name is Stromer. So heroic things were done early on, but it was really, really hard to do them. Now the basic idea it's always the problem with this course. I teach you mathematics that we actually don't use, but it's a, you know, good step. So the basic idea is due to, guess who? Euler. who had to do these integrations very early on. And I'll get to it in a second, but the kind of things we use in this course as example of dynamical systems are ordinary, a fancier version of harmonic oscillator. So in a harmonic oscillator, you have an acceleration term. And now you can think of this x as time. So the second derivative of displacement y is, where is the particle? And Newton says that should be proportional, and that force might change this time. Kind of Aristotle or wrong physics, Hellenistic physics says, well, friction very important. Intuitively, that's correct. So there is a first derivative with respect to time, and the friction might or might depend on time. So just a random example of 1,000 equations that you have to solve. So this is friction and this is acceleration. And there are many ways to solve this equation, but in this dynamical systems, we find it convenient to think of dynamics being described by a vector over our state space. In this case, Hamilton gave us the way to do this, but it doesn't have to have anything to do with Hamilton. So one strategy when you have higher derivatives in your equations is to convert them into first derivatives by introducing new functions. So you just call this first derivative, call it the new function, z. Because if you have function y, then and it's a analytic function, you'll be able to write it as its derivative as a function. And then this z, its derivative is this quantity here. That you can now write as the forcing. And then you can put this guy on the left-hand side, minus q of x times the derivative, but that's what this function is. So one thing that we often do, but it might not be a very smart thing, you really have to understand it in the context of any particular problem. We can convert ordinary differential equations into, in this case, two-dimensional field. So if I have my manifold state space, so all values of y and z, then at every point in that state space, I will have a one-dimension, in this case, two-dimensional vector, but it could be any number of dimensions. Ordinary differential equations having some manifold, and on that, which we call state space, and for any value of the functions on this state space, there is an associate velocity, generalized notion of velocity, a vector field. That's a convenient way of thinking of dynamics. And now what you're supposed to do is you're supposed to make predictions. So you're supposed to, if you start at any of these points, with this decimal increment of your parameter, your time in this case, let's say, you get an infinitesimal change in all components that describe your state space, in this case, y and z, time, delta x. Later you will find yourself someplace. In general, this trajectory is small. I mean, this trajectory is a nonlinear function, so you don't just move on straight. It's your linear approximation for small time where you move, and your long time prediction will be some trajectory. One of the ways in general to compute is to piece together small steps, go in infinitesimal steps, and every step you recompute your little vector and your step, and you keep going. And this is a very human way of thinking of how to solve these equations, because in our mind, Newton's mind, and until way we thought about space and time until beginning of 20th century, space is this thing here, it's a room. Time, I have some biological clock and I'm changing in time. So for us, time is immensely physical experience. We are locked in time, and it's very hard for us to think of any other way than stepping forward in time. So this seems very natural. It'll turn out that in theory that will develop now nonlinear systems in the last third of the course, this might seem natural, but the consequences will be exponentially bad, because we'll find out that thinking this way, we are only able to predict for a finite time, because we'll find that trajectories are unstable, our errors grow exponentially, and things go to hell. Now, already in late 18th century and beginning of 19th century, there was an alternative way of thinking about it. An alternative way of thinking about it was to say, I shouldn't just start and blindly walk and see where it gets me. I should say that if I'm here and I want to go to the chair's office, I should find out an optimal way of getting there. That's called variational principles, and it leads in mechanics, this way of thinking. You're always taught as Hamilton's equation. And the idea is that if you replace where you are, if you supplement it by information how you're moving, so this is position, and in mechanics this is called momentum, this pair of equations is an elegant way of thinking how I move as time changes. Now, I won't write it in detail, but duty bound to misspell this. Maupertuis, etc. They found, and then in particular Lagrange, which was pretty amazing. It was so amazing that Maupertuis believed it was proof of existence of God. He was Lagrange was a working foreigner, immigrant in France, so he was just. What you should do is you should be totally opportunistic and use anything that works at any given time, and not attach to any of these approaches religious significance. I advise total opposite. Whatever method works, try it and then try to understand it, and maybe you'll improve it. And the amazing thing about this kind of subject is that basic ideas, the first idea you would think of, like Euler's idea, was figured out in 18th century. An improvement which is called Runge-Kutta, which I'll sketch out today, was done in 1900. Now today, every 5 or 10 years, some applied mathematician or engineer or somebody invents a new and better method, for a particular subset of problem. So this just goes on. I mean, one of the most amazing things that happened in kind of 1780s is something called fast Fourier transform. So, when they teach you, it's totally trivial. I do this, I invert some matrix. If it's, tridiagonal, it works. If it's in powers of 2 or 3, etc. It's only invented 2030, and that's what we use. So I'm for two-step things. I just get best advice for anybody. I don't care who. As done, chemists have to solve difficult problems. Engineers do. And then I try to understand why the method works. And sometimes, if you're lucky, you can improve it in a significant way. But I will just sketch out what I think are some main ideas behind numerical analysis in this thing that, subject is vast. So all I want to say in this lecture is, we as humans want to do this. I mean, just a totally human thing. But actually, equations don't care that we are human. Equations just want to be solved. First, Maupertuis and Lagrange did. They did something that seemed totally criminal. They said, well, I'm here at, for example, I'm a soldier and I want to lob a projectile across some trenches to someplace, right? So I have a goal. One way I can do this is I can make few errors until I improve it. But they did something totally crazy. They said, well, suppose your bomb goes this way. A thing that nature doesn't do, They chose some weird path from here to there, and they associated, and they said, look, I'm lazy, I would like to, work as little as possible to get my job done. So they associated a function with this called, has various names, action, work, whatever. So they said, if I go this way and I measure, how much I have to push around to move around, I integrate the work I've done, and I find to associate to each path a function, one number, just one number. And then they say, well, if I find the cheapest way of getting from here to there, it'll have a property that if I go a little bit to the left of the cheapest way, it'll get more expensive. If I go a little bit to the right of cheapest way, it'll go more expensive. So as long as this cost function is smooth, and we're used to things being polynomials and God knows what, smooth functions, I should be down at the bottom of this thing. And that's a good way of going from here to there because it's the cheapest way. And now it turns out that the bottom, which is called extremum, it could be also the top, doesn't it? Gives you Lagrange Euler equations. And when you look at them, you realize they're very much like Hamilton's equation, but instead of using momentum, I'm using position and velocity. So what's the big deal? And you learn this in mechanics and fine. And it's a sort of strange thing that teach you in mechanics, because they tell you that you just go any place where law doesn't allow you to go. And all you get out of it in mechanics course is the equations you already know, which are Hamilton's equation, just written in a weird way because velocity is now written as momentum, which is mass time velocity. So you might ask, what the hell is this and why are they teaching me this? Because I already know these equations. These ones look more like original Newton's equation, because being down at the bottom, you get the second derivatives and stuff like that. So that's how we learn it in mechanics. Now, the reason why we have to teach you this in mechanics today is something that happens 120 years later, which is quantum mechanics. For some reason, quantum mechanics allows you to stray away from allowed paths. You have to add up all these possible paths, and that's called path integrals, and it's foundational. It's how quantum mechanics works. These guys knew nothing about quantum mechanics. They knew about waves. So Hamilton first did geometrical optics before he realized his equations of mechanics. If you start with Newton saying acceleration equals force, you'll never invent quantum mechanics. If you start Maupertuis, Lagrangian, variational action principles, you will make some prediction, and that'll turn out to be quantum mechanics. And it took us a long time to understand it from various ways. So it's Dirac and Feynman who reformulated this way. The original version was, more like Hamilton's equations due to Schrödinger, etc. So this is all very abstract. This makes total sense. This, sounds plausible. I said nature likes to be as lazy as possible, so there is some function which is, the least costly way of getting from here to there. And that makes it sound like engineering. I have to program something in such a way that I move stuff around, and either I deliver it as fast as possible, or I work as little as possible, and the cost is less, etc. So it turns out that while by we I mean people like physicists, really think this way, if you're a good engineer, they all think like this. If you do robotics, you think like this. And that actually was Lagrange's attitude. He found out that this is hard to solve if you have funny boundary conditions or constraints. But if you use this formulation, it's a very natural way of putting constraints in, etc. Now today, when you try to solve various problems numerically, this way of solving for finding solutions of equations might be much smarter than this way, which seems natural to you. So what is this way? It says that an allowed deterministic, by deterministic I mean it has these equations of motion in which you have unique trajectory, there is no noise, no quantum mechanics, nothing deterministic. Allowed deterministic equation has a property that every step along the way, and this is, you don't get this emphasized when they teach you variational Lagrangian principles. Every step of the way, locally, I must obey the law. So what you're saying is, I will look at all possible one-dimensional curves, spaghetti I can put in my state space, but I'll allow only the ones that every place obey the law locally. So you have to check. And then they satisfy boundary conditions, They start where I wanted to start, they end where I want to end.
What's the difference there?
When you are at any point in your world of, state space, you can make a little linear chart whose size is, maybe dt and dx. So much in time, so much in space, but the little chart. And that's actually what these equations are. They're just telling you locally, as I move a little bit, I'm on, in one dimension, I'm moving along a straight line, even though the true trajectory will be something nonlinear. And in higher dimension, and for partial differential equations, and for more complicated problems, like problems of distinguishing cats from dogs, etc., on light sets, you just have to make local means that on a infinitesimal, or in practice your discretization level, you're obeying the law. Now, the reason why Lagrange, Maupertuis, and everybody until this millennium basically didn't do this, because this seems very expensive. Hamiltonian formulation seems economical to us because, we start at a state which is finitely specified. Say, let's say my state space is 7-dimensional, and then we have a little machinery that just crunches out a trajectory. So to understand this whole orbit, this whole where I can end up, I only need to know where I am plus my little crank that produces the thing. Whereas this says I discretize my trajectory, I put 1,000 points on it. So now I'm in a 1,000-dimensional space, so I need memory to contain this. And then I vary everybody and just make sure that I'm at the bottom of the valley. If I think in this way, at extremum at all points. So this was totally undoable until now. These little local elements are very cheap. If you do fluid dynamics in 3 spatial dimension, 1 time dimension, you can make a grid, and you can put a processor on each grid, and they're cheap. We have reached the limit of processing speed, but we have lots of processors to put in. So this actually, in future, might be the way how you solve climate and various equations which are very high dimensional, because these guys are getting cheap. So today, even though in this course we only teach you that, what we actually do today, problems like this, solve them in engineering by writing a cost function which says, how much I'm penalized if I go away from my optimal path. In mechanics, that's called Lagrangian. The cost function in that case is well defined, but in engineering, you have all kinds of objectives and goals to do, and they don't have, there is no Lagrangian description necessarily. This is how to solve this problem. So I will teach you this, but this is what we actually do today. When you're interested, it depends on the problem. Again, you're opportunistic. By the end of the course, I'll show you this doesn't make any sense. There's a 50-50 chance if you look at your nonlinear problem, doesn't matter, what is your research project as a graduate student or research scientist, there's a 50-50 chance that when you look locally what happens to the neighboring trajectories, they can either kind of wrap around your trajectory or they can run away exponentially, because the linear equations in these neighborhoods have 2 kinds of solutions. They're either exponentials or imaginary exponential oscillating functions, or some mixture of 2. So it's kind of 50-50, in particular problem. It might turn out it's really good to think like in, short time celestial mechanics. It's really good to do this. It works very well. Errors don't grow. And in turbulence and in many other nonlinear problems, you find out this thing falls apart very soon. There's a horizon of prediction. It has a name of man who didn't think of it. It's called Lyapunov, some nobleman in Russia at beginning of 20th century. No computer can beat it because no computer can beat exponentials. Nothing beats exponentials, unless you rein them in by some other way. Now, these methods, due to Lagrange variational methods, have a property that you don't move at all. You just check at every step, is the law obeyed or not? So they don't have this problem of exploding exponentially, being unstable. You just have to find it, optimize it, and put. So these are two. There are few problems, and in some sense, there is only one problem you can solve analytically. And it has a zillion names, but basically it's harmonic oscillator. So for example, when you solve Kepler problems, it looks very different because it has ellipses as solution. But there is a mapping in which you rescale the time and it becomes a circle. And now there are lots of problems in higher dimension that kind of look like fancier oscillators. And it's a branch of mathematical physics called integrable systems. And the point of integrable systems is that you work hard with nonlinear transformation of this and that, and your difficult equations I show, it's a bunch of equations, each one running on a circle. In that case, if you run a circle, you know where you are because you know the radius of the circle, and you just have to keep time. Now, in a world of problems that you care about, they're like integers among normal numbers. They sometimes exist. They exist in surprising places. They can be beautiful. You use lots of symmetries, algebras, all kinds of beautiful things. Religious people like quantum field theorists, have a running bet whether the fundamental truth is integrable or not. To me it seems totally insane, but people have money on it. I'll give you a bottle of champagne if you show that fundamental equations of nature are integrable. They can be all written in terms of running on circles. I'm not in that religion myself, or any religion, but it's a constant thing. And now, in course I'll teach, that's one extreme, that's called integrable. But people have understood I should also look at situation where, if I perturb the system, it doesn't just ring in little circles. That's, for example, if I'm at the Lagrange point and I put my telescope at Lagrange point, it's balanced, the gravity is balanced between sun, Earth, Moon, and Sun. But if I drift a little bit around, I'll start oscillating around that point. So that's kind of generic thing you think of. Integrable systems is that the perturbations don't grow. They just kind of take care of themselves. But if I'm top of the mountain, I step a little bit, I just start running down. There is no way, to stay in that neighborhood. And there is another world of systems which are ergodic or Fourier chaotic, which have a property that no matter where I start, there is no safe haven. I'm constantly forced to move around, and my neighbors go away from me. Nothing stays together. And it turns out this is as special and as rare as integrable systems. You really have to do amazing thing, finding ergodic systems that where you can prove that there is no region in which my errors are oscillatory, small. That's maybe even harder than finding integrable systems. And in my opinion, the world that we have to explore is the world of in between these extremes. But these ideas of possible extreme behaviors, help you choose numerical method for your particular problem. Now, today, no matter what you do, you discretize of this and that. It might be a very large number, but it's always finite. So the question is always how to discretize in a smart way. So one is, what's in the word discretize. You replace the space by a bunch of points, for example, centers of tiles that cover your floor, and you produce some kind of mesh. And we'll do this in one dimension when we do Euler's way of integrating ordinary differential equation, but in general, this is in some number of dimensions. Grid, lattice, there are different words for this kind of discretizations of your state space. And by mesh, we mean, sometimes it's important. There are regions of my state space where there is not much change. Things are moving smoothly, no big deal. So I don't need to put many points there, but then there are some corners where things really get complicated and twisted. I have to populate it with more. So there is a whole technology of how you improve your meshes, but testing your cost functions and seeing where they vary and put more points. And the lattices are usually very regular. And in lattices, you get in a situation where the symmetries of your lattice are very helpful in simplifying the calculation. But that's what they are. Now the second set of methods, I don't know where this is fair, but I think it starts with Fourier, a French military engineer who was trying to describe heat equation, which is how heat propagates through material. And he realized that the way that this develops is very smooth. And instead of evaluating what happens at this point, this point, this point, which is what you do in discretization, he realized that, this almost looks like sine function, but not quite, which means I have to use a higher harmonic. And I fix it here, but then there is something happening there. And if I have smooth functions, instead of discretizing them, it might be much better to go to what's called spectral methods. Which is saying, my problem has some basic symmetry, so the natural basis is some functions. If I look at, whatever, my field over, this is space, and maybe time, that a good way to do this is to find a basis function, bunch of functions. So I write it as a sum of smooth things. If I choose a good basis, and that's what the theory of Fourier functions, orthogonal polynomials, and much mathematics you run in is figuring out how to compute these coefficients efficiently. And now what happens? Discretization has a very different flavor. It's a truncation in how many functions you use. So maybe you go from, I don't know, n functions, and there is some symmetry, and God knows what. So n ranges. And that's very powerful. Lots of fluid dynamics is done in various bases. This could be, the simplest thing is, of course, exponentials, so they could be Fourier modes. Well, yeah, sines and cosines. Or they could be, Chebyshev. Or they could be Hermite polynomials. And each one of them is designed for special class of problems. So for example, if you're preparing something for experiment, and for you it's easiest to produce packages that look like Gaussian packages that are most likely to be at the point you want to have your particle, but then there is some distribution, then Hermite polynomials will be the natural basis for things that look like. So this is specific. You work it out for every problem. It's very different. But when you're very lucky, so for example, with Fourier polynomials, you can estimate the error you make by using some number of these bases. And for these Fourier polynomials, you discover that it's falling off exponentially. So it means, you use 10 of them, but the error is, 2 to the minus 10 or something. So it turns out, depending on the problem, this kind of spectral method might be your choice. And then when you look at it carefully and opportunistically, you discover, part of your function is naturally expanded in smooth functions, but the other part should be discretized on regression. That's called pseudo-spectral methods. And that's what you will often see. There'll be some opportunistic thing where nonlinear terms are easiest to compute on a space mesh, whereas kinetic terms, derivatives, etc., easiest to compute in this basis. And that's what you actually do. So you always go finite, you always truncate. But how you do it is very much dependent on the nature of your problem.